You got undergrad master? Yeah.
I don't think we can stand here.
No. Authoritarian.
This thing doesn't steer. It is what it is.
It's not like the regular wheelchair, we have to put on the wheel and kind of.
I know. I got it small so it would go in a trunk, but hello, everyone. We're about ready to get started, so please take your seat. So hello, everyone. I'm Jan Rush. I'm president of the DVAA, and I'm sitting today because in solidarity with our program chair, Jeremy, I broke my 5th metatarsal on my right foot, which is the same bone he broke. So I hope he appreciates this act of solidarity.
Limping for office.
So I always like to start with talking a little bit about some accomplishments that we have to think about. Maybe some of you, hey, Brian, could you get the lights down, please? Maybe some of you saw this note from Dan Stern. He apparently discovered a new planetary nebula, or believes he did, which is cool to have a member discover something brand new. You can see where it's located here in Sagittarius. That's not what I meant to do. Right there. And here's what the object looks like. Really, really dim, really far away. If you'd like to imagine where this is in the sky, we don't very often look at Sagittarius because it's kind of a dim constellation, but it's here in the neighborhood of a lot of stuff we know: Hercules, Lyra, Delphinus, and Sagitta is the arrow that Hercules used to strike down the eagle that Zeus sent to gnaw Prometheus's liver. And if you're into Greek mythology, this particular image took 91 hours of exposure across visual hydrogen alpha and O3 wavelengths. It's very small and faint, and Dan says it is measuring roughly 5 × 11 arc seconds, which is the angular size of a human hair seen from 3 meters or 10 feet away. So really, really tiny, very dim. But you can't just discover a planetary and declare it. So he has now sent the data to the gatekeeper, where there's a planetary expert in France who declares whether it is indeed a planetary nebula. And it is, there was no central star identified. So that's a little bit atypical, but may still be the right one. We will wait to see. And some of you may have heard that there's a new supernova in the Deerlick galaxy. So we had a lot of people imaging the Deerlick galaxy this month. And this GIF is from Tom Nolasco. So right here, you can see where the supernova is, this little bright spot there where it looks like the galaxy has a double core. When I first heard about supernovae, I was really new to astronomy, and I went out and I thought they were just going to blaze all over the sky. But obviously you can see it's very subtle, hard to find, and we really appreciate this gift from Tom for pointing it out to us. And speaking of famous people, Tom again was honored by this photo, this image of coronal rain, which got published just this month in Sky and Telescope. Yeah, so look at this stuff. It comes off the surface of the sun and then gets captured and goes down like rain. So interesting. Take a look at Sky and Telescope for more detailed pictures. Also, we have to mention our honor of the second win of the newsletter award for the Mabel Stearns Award from the Astronomical League. So I have right now a plaque to present to Ken Kopplinger for winning this year's award. Look at this. It's amazing.
Beautiful.
Yes, it's beautiful. I know. I'm not going to turn too far. Congratulations.
Thank you.
Got a brilliant rip it for me.
And Ken, you did some cool things to come up with this issue. You want to mention any of that?
Yeah, I always like to when I serve as the editor for the month, I always like to kind of have a theme. I guess I don't like to have this different things. I like to think sort of a grand theme. So I think for this issue, I really talked about galaxies and, you know, how did we know galaxies other than our own galaxy actually exists, and talked a little bit about the history of that. And you know, it's actually a lot of work. I think any of us that are on the newsletter committee know it's quite a bit of work to put these issues together. And so we always appreciate the comments that we hear from people afterwards. It's very appreciated. Some of us are kind of geeks and like to write. And so after I've retired, it gives me some writing output. So anyway, thank you.
Thank you very much for all your hard work. Everybody on the committee for their hard work. Yeah, this is the third time we've won first place. 2014 was Carl Henry, right? 2024 was Tom Nolasco, and now we have 2025. And then in addition, George and Tom jointly won for third place in 2022. So we are really, really up there. We're the ones to beat. And one more club award. Congratulations to Bob Madeiri, who won second place in the optical competition at Stellafane. There he is with his Newtonian reflector. Okay. All right, now to the upcoming events. I mentioned last week, I believe, that next month's meeting will be not here in this room, will be instead at Fort Washington State Park. And this is our annual picnic that we've been having for about 5 years. There'll be food, there'll be fellowship. We stick around after dinner to do some observing in the adjacent field. It's a lot of fun. Everything is free. And this year, we're going to try astronomy trivia. And don't worry, it's not all astrophysics. We got other stuff in there. We got sci-fi, we got DVAA history, we got space news. So come one, come all, and have some fun with astronomy trivia. Okay, these are the events that are coming. Ooh, wow, what did I do? I got my Buddha. These are the events that are coming up this month, or the next few weeks. This is something interesting. It was sent to me by a non-member. On August 10th, there's a documentary on the James Webb Space Telescope at the Ambler Theater. It's one showing at 4 o'clock, but it's going to be introduced by James Traley, who is the filmmaker, and he's from Ambler. So he's going to answer questions and introduce it. So it should be good. On August 12th is our usual, August 12th is a special star party at Fort Washington State Park. And Ken, would you like to say anything about that?
Yeah, we're gonna do this Fort Washington Star Party in support of Fort Washington State Park. They allow us to use the park for other events, and so we do this to help them out. So we're still needing. If you go on their website, you'll see that it says the registration is closed, that it's full, but that doesn't apply to us. We still need telescope and telescope operators to come out. So you could ignore, I've had a few emails asking me if you can still come out. Yeah, please do. I've been bending some arms tonight. Get some folks to come out. I'll pay you double what I normally pay. It doesn't add up to much.
Are people gonna have arm braces next time?
Yeah, you gotta watch out. If you don't volunteer, we'll have to come and bend some arms. So anyway, we do, I encourage you. I don't know if people are, not willing or a little bit bashful or whatever, but we need people to volunteer for these things. We also have something on August 22nd I wanted to mention. We're actually partnering with, by the way, is Hallie here tonight? Hallie Thomas? I guess not. Holly Thomas runs the Malali Exxon Malali Association. It's an Indian Heritage Foundation, from my understanding. And they've asked us, he's a DVAA member, and he's asked us to come out and help them out with a lot of young folks that are very interested in astronomy. So we're gonna meet over, this is kind of new for us, we're gonna meet over at Marsh Creek State Park. So I know many of you might live over that way. Please come out and help us. Give me if you could send me a note to tell me that you can come out, I'd appreciate it, because we got to make sure that we have enough people to bring telescopes, because a lot of youngsters would like to look through telescopes. So anyway, thank you. I'm kind of excited about this. By the way, that's on the west side of Marsh Creek State Park. It's a new trailhead that was just put in there off of what's the name of the road? I can't remember. I don't remember the name of the road, but there's a new trailhead there. I'll put it on the website. So I'm hoping that we get some good turnout for this to help out the young folks that are interested in astronomy.
Okay, thank you. August 13th, we have a solar viewing for kids event at North Wales Library, and Barry Johnson is heading that up. Barry, anything you want to say about that?
Well, we have 2 telescopes so far, so that should do it.
Two so far, okay.
So if you have a solar filter and that afternoon off, so that's why you join us.
Yeah, it's a nice event. We've been doing it several years, and the kids really love it. Okay, down on the list, August 30th is our public star party at Valley Forge. And I put on here Signal Seekers Model Airplane Field. It's not a new place. It's just that I realized that if you put Signal Seekers, which is the official name of the Model Airplane Club, if you put that in Google, it takes you exactly to the right spot. So something good to know. Astrophotography workshop by Zoom on September 3rd. The full moon hike and public viewing at Green Lane Park. That's something that Craig and Tracy Block are leading. And if you're in the area of Green Lane, it'd be great to have you join up. What they do is the ranger is leading a hike, and they use the light of the full moon to do their hike. And at the end of the hike, they look through the telescopes at the moon. So lots of fun. And last but not least is the annual DVAA picnic, which I already told you about at Fort Washington State Park. And if you need to know where that is, the event on the website it's easy to find all the directions of how to get there. We're in pavilion number 3. So. Okay, we have a few announcements now from our welcoming chair, Brian Lee.
I'm Brian Lee, welcoming chair for the DVAA. We have 5 new members this month. Darren Breslin, Daniel McCauley, Joseph Gelda, Frank Noonian, and Merle Al. I don't believe they're here tonight, but let's give them a hand.
Okay, and I always like to ask, who's here for the first time tonight? Oh, wow, that's a lot. Yes, great. Yeah, come up and say hello. I'm not very mobile to get around to people, but come up and say hello. Okay, some announcements from the astrophotography group. I don't think I saw John here though, did I? Okay. So Gary Trabazano, who's the astrophotography chair, couldn't be here tonight, so he gave me a couple slides to present. We've made a little change, he's made a little change in the usual agenda for the astrophotography workshops that happen the Wednesday prior to the regular monthly meetings. They're going to have a special dedicated beginner session that will come first before the main meeting. So if you're a beginning imager and you'd like to get some questions answered, dial in early at 7 o'clock, and that's the time reserved for you. Then the usual agenda they follow is that ask for any new attendees to the meeting, find out where you are on your imaging journey or your astronomy journey, and then do Q&A. And then sometimes there is a specific presentation on a specific topic. So that's generally the agenda that is going to be followed. And these are open to anyone. So please, if you'd like to just know a little more about imaging, know a little bit more to meet people that do it and find out more about the equipment, you're welcome to dial in. The way you find it, just go to DVAA events and click on Astrophotography Workshop, and you'll find the link, the Zoom link, so that you can get right into the meeting. Okay, now we have a presentation from our third place winner of the DVA Youth Awards. So I'd like to introduce Claire Lynch, or invite Claire Lynch to come up. She's a sophomore at Springside Chestnut Hill Academy, and her topic is on Radio is Stellar, the Sun's Effect on Radio Transmission. So let's here. The camera is over here, so kind of stand there, and you need a pointer. This is the laser pointer, and this goes forward and this goes back.
It's the opposite
They're
of what you think.
opposite, yes. Do you have a pocket? No. Okay. I can hold it. Okay.
The camera's right here.
Stand there.
All right. Hi, my name is Claire Lynch. This is my project, Radio is Stellar. It's a look into time of day and specifically the sun's effect on radio transmissions. So I got my amateur radio license just this fall. I initially got it for my school's high altitude ballooning program, but as I was going through the ham radio training, I realized there was some other cool stuff that could be done with it. One of the first things they tell you.
It's on. It's off. Works better when it's on.
One of the first things they tell you is that you can contact the International Space Station using ham radio. And it's kind of like, I was like, what? And then you realize like you can make so many connections, not only with space, but with other people in the real world. It goes beyond just tracking your little balloon in the sky. So I wanted to see what I could do, the people I could connect with, and find the correlation between time of day and radio waves. Essentially, I was asking what frequencies are best to use when, and how are they affected by time of day, different types of propagation through the atmosphere as time of day changes, and stuff like that. So first, I was looking at what are radio waves exactly. I'm sure many of you know, radio waves are a type of electromagnetic wave that consist of two oscillating fields. And radio waves can span anywhere from 1 centimeter to 10 kilometers. So it's a pretty wide range. And like they have different purposes, different wavelengths have different purposes. So I want to see like what really is going on here, what is best to use here on Earth to connect with other people on Earth. The way a radio wave interacts with the atmosphere is dependent on its wavelength. As wavelength, so a bandwidth is a group of frequencies that loosely correlate to a wavelength, and the relationship is wavelength equals velocity of frequency, and the velocity is the speed of light. And like I was talking about, propagation occurs in the space and the atmosphere called the ionosphere. The ionosphere is in between space and the regular atmosphere, and it consists of charged particles that are ionized by the sun's energy. This is where radio waves are bent and can be sent signals can be sent way farther, even if they're just weak signals, they can be sent extremely far through the ionosphere because of these charged particles, but also makes it really reactive to space weather. So there can be a lot of disturbances, and it can affect your signals and make your ability to connect with people less consistent. The bottom layer of the ionosphere is called the D layer. It's the lowest region, and it actually disappears at night. So when the sun goes down, the ionized particles just become regular oxygen particles, and they're no longer charged or able to create radio wave propagation. The D layer absorbs radio waves during the day. So when it's present, radio waves cannot get through unless they're strong. So it absorbs most radio waves. It makes for a really strong clear signals during the day, but it stops most weak signals from reaching the E and F layer of the ionosphere, which are the higher layers, where they can really be bent and sent far. Gray line propagation is a result of this phenomenon where between the day and night, the F layer is perfectly like just as ionized as any point in the day, but the D layer actually disappears because of the angle the sun is hitting the Earth's atmosphere. It is focusing its energy on the F layer, but not on the D layer at all. So it disappears and allows you to get that full ionized effect with the E and F layer while not having any prevention from the D layer. Another downside of daytime is that means facing the effects of solar activity. Earth's magnetic sphere is actually uneven. The side of Earth's magnetic sphere that's facing the sun is much smaller than the side that is the nighttime side or the side facing away because pressure, the pressure from the sun compresses it. So it's easier for effects of solar weather like particles, plasma, and radiation to get into the atmosphere during the day when you're facing the sun. This has an effect on solar propagation, which is another type of propagation, essentially using the E and F layers. If your signal does manage to get through that D layer during the day, it'll have extremely strong ionization in the E and F layers because of the sun. But it can also be a little iffy if your frequency is too high or too low. You have to find the right place for it to really be bent and go where you would like it to. Can lead to noisy band conditions and difficulty transmitting when there's an excess of solar activity and space weather. We recently passed a solar peak. So the way the Earth's magnetic sphere or sun's magnetic sphere works, there's multiple of them and they move at different speeds. So they get kind of mixed up and it creates a lot of space weather around an 11-year peak. So that can have an effect on solar propagation, which I was looking at. When I did the project, it was around that peak. So I was keeping that in mind and looking at inconsistencies in radio waves' ability to travel. My hypothesis, there's a lot of different factors to consider. I thought the 10-meter band would go the furthest during all times of day, and all the bands would go the furthest during sunset and sunrise. I thought the 30-meter band would see the least difference depending on time of day. So the times I'm looking at are midnight, sunrise, noon, and sunset, but I looked at sunrise and sunset in the central time zone because I was looking exclusively at the United States of America because I wanted to avoid any cultural differences on what bands are used by hams. So I thought the 30-meter band would travel the least distance at all times. The 20-meter band would be the middle ground on both fronts, but again, have the easiest time with gray line propagation, that sort of perfect middle ground moment. And I thought the 10-meter band would travel the furthest, further than the rest. So my procedure involved a website called WhisperNet, stands for Weak Signal Propagation Network, and it's a place where hams can put all the weak signals they successfully propagated and made connections with into a website. They log it. So I logged onto the website at all 4 of those times a day, and I took screenshots of the map and so recorded my initial impressions of each bandwidth of 10, 20, and 30 meters to see the busyness of the bands. And also I looked at the longest transmissions. So I used process of elimination and kept setting the minimum distance up to see what the longest transmission would be for each band at each time. I did this 4 times a day for 10 days within a few weeks for consistency because space weather changes. Weather on Earth also has an effect. I wanted to avoid drastic differences in that. And then I compared and analyzed my data. So this is an example of how I collected the data for the busyness of the bands. Whisper has an overload setting. If there's more than 500 entries for one band within a time period, I did 10 minutes, it overloads. So I would record overloads. If it was just busy or sort of in the middle ground, I marked that. And then it's not in this picture, but there were moments when it was completely dead. There was 1 or 2 transmissions being made on that band. I just thought that I would look at what other hams were doing, because they know their stuff, like they know what they're doing, so if they're using it, it's probably a good time to be being used. I also looked at longest transmissions. I recorded where it was going, where it was from, and how the approximate length of the transmission. I did this for each band at each time of day. This is how I documented my data, so I made sure that there wasn't any like tricks of the eye. I was saying I took screenshots of each time I was doing it, and this is what the Whisper website looks like. So you can see that there's a big difference. A lot here when it was daytime, there was a lot more usage. I believe this is a 20-meter band, and then at nighttime there was a lot less. I would consider this busy but not overloaded. So that's just a look at like my process of determining what was going on. This is the data. So this is for the busyness of bands. It was on a scale of 0 to 3. And as you can see, the 30-meter and 20-meter bands were being used pretty consistently at all times of day. Because the 10-meter band really just fell off in the middle of the night, and it was being used a lot during sunrise, noon, and sunset. And then you see sunrise and sunset have the most usage because of that gray line propagation. It's really a time to be using the waves, using that to your advantage. I used standard deviation to look at the consistency of the bands and also their ability to take advantage of specific types of propagation and the consistency of those types of propagation. So at noon, there's higher deviations, and that could just be due to, honestly, days of the week, but also different things like how well the solar propagation was working. Maybe with solar activity, it was a little less reliable. And then here in longest transmissions. So you can see that the first, second, and third, the longest transmissions, are consistent at every point of day. Sunrise and sunset had the most. It's 20-meter first, 30-meter second, 10-meter third, and it follows the same pattern. The longest transmission was the 20-meter band at sunrise, which is 18,805 kilometers. That's almost halfway across the globe. So, and these are all weak signals. None of these are like really strong, powerful antennas. They're all weak signals coming from hams that are being propagated through the atmosphere. I also looked at standard deviation for the longest transmissions. And you can see that the 10-meter band actually has the largest standard deviation in all of the times of day but noon. This could be attributed to its lack of ability to consistently take advantage of all the different types of propagation. And also the sunrise and sunset have the least deviation in the data, which indicates that gray line propagation is the most reliable type of propagation. I have a video here. It's kind of iffy. It doesn't show up sometimes. But I put all of the data onto a Google map, all the longest transmissions, onto Google Earth, and so you could see them all. And it's just, again, with the some of them, I think one reached 20,000 kilometers, which is halfway across the Earth. It's just like really a really amazing process, and how the atmosphere has this much effect and power to take little signals far. Yeah, here it is.
Like inside it.
Up here.
You can see they're color coded to their band and type of day. All the pinks are 10 meters, the greens are 30 meters, and the yellows are 20 meters. And then the level, like their shade, is their type of day. People making connections across continents and all over. It was just a cool visual to see. So, conclusion. The 10-meter band actually had the shortest transmissions as opposed to what I thought would be the longest. And it was dead at night and overloaded during the day. I thought it would have be moderately affected by time of day and the sun. The 20-meter band was not the middle ground, as expected. It was actually the longest transmissions and frequently the most busy. Whereas the 30-meter band was not the weakest, but instead the middle ground, leaning more towards the 20-meter band than 10-meter band. 10-meter band really stands alone in its inability to go far. The sunset and sunrise consistently the longest transmissions, really stressing that gray line propagation as the best of both worlds. Midnight had the shortest, and noon was in the middle, but a lot closer to midnight. And they both have these flaws where midnight, none of the ionosphere is really as ionized as it could be, and noon, none of the radio signal, or very few of the weak signals can get through the D layer and get to the E and F layer. So which band is best when? When can you go the furthest and get the most out of your transmission? And it's the 20-meter band at sunrise and sunset. The furthest propagation events occur, and the bands are super busy for making connections with other people. It makes sense because higher frequencies are bent less in the atmosphere, which means they go further. However, there is a maximum usable frequency where frequencies that are too high can get lost. They can go out into space if they are not bent soon enough. So it gives it a long range. And so 20-meter band as the middle is the best. It's not too high. It's never the maximum usable frequency. And it's not too low, so it's still bent very far. Want to change? I'd love to cut down on time for this project, just because the website Whisper, unless you're like a member of the website, it doesn't collect data for you, so you have to go on each time and get it yourself. And a resource that doesn't overload or counts transmissions, get a numerical value for the busyness of bands, as opposed to like there's error and just using the human eye to look at it. I also like to analyze individual data points as opposed to averages, and look at bandwidths that are further apart. 10, 20, and 30 are all pretty close together. They are common ham radio frequencies, but to just see bigger differences. And these are my sources. Thank you. Oh man, I'm working on coming up with some. I'm using we're building our own radio telescope at school. But also I have access to the Green Bank Observatory's radio telescope, which is a little bigger than the cardboard one in our lab. That you can use to I have access to, and I can image items. I might be looking at pulsars, which are really useful. They can tell different things. They've helped prove gravitational waves as a theory. So I might be looking at pulsars. I don't have concrete plans, but I will be doing an independent research project and somewhere along those lines.
Fantastic.
What class license do you currently have?
I'm a technician.
Okay, I'd like to invite Al up to present her certificate.
Real quick, I just want to present Claire with the her certificate from as the third place winner for the 2025 DVAA Youth Award, as well as a small check to support her hobby for the coming year.
One more.
Be the next most usually.
Thank you very, very much. That was great. Very impressive work. Okay, now I'd like to hand over to Jeremy, who will introduce our main presenter, featured presenter.
All right, thanks, Jen. So I've been looking forward to this presentation for a while. Don McCallernan has been a longtime DVAA member. How many years?
1986, I joined.
Since 1986. All right, that's about as long as I've been in astronomy. Maybe a little longer, but haven't been around here as long as that. Yeah, so Don's been a longtime DVAA member, and his main interest has been radio astronomy. Right, so we all deal with light pollution and having to get to dark sky sites. Well, this is a way around that, and you can also observe during the day. So I've been looking forward to having him for quite a while, but other things have always been getting in the way. But Don is retired now, so that eliminates one of those things that gets in the way of quality astronomy time. So please join me in welcoming Don McCallernan to talk about radio astronomy, how he does it at home.
Yeah. Or should I just use I can use this as a clip thing. Okay, on the wrong side. There we go.
Did you have notes on here?
No.
You didn't.
that's-
All right, are you ready?
This is my pocket. Make sure. Okay, here we go. Laser, yeah, okay. All right, thank you, everybody, for having me tonight. I'd like to thank Jeremy, Jan, Tom, and the entire DVAA for inviting me tonight to do this talk. I've done this talk similar back in 2003 at the Schuylkill Valley Nature Center. And a lot of new faces, but there are a lot of faces in here tonight that were back at that presentation in 2003. So this club is amazing in its longevity and how it keeps going on strong. And I'm proud of that, proud to be a member. So I'm here to talk tonight about backyard radio telescope that you can receive low frequency radio missions from the planet Jupiter, the sun, and our galaxy. So let me just make sure that's clicking right here. Yeah, here we go. Okay, so I'm going to start out. There's 3 sections in my talk. It's going to be theory, then there's going to be construction of the radio telescope, and then there's going to be the operation. So we're going to start out with first is theory. And theory is going to be broken down into 4 sections. And I'm going to be going fast here because I'm going to be skimming the surface on these topics. I'm not going to be doing a deep dive into them. But we're going to talk briefly on the electromagnetic spectrum. And then we're going to talk about Jupiter missions and a little bit on solar flares. But Claire did do a lot on that. And thank you, Claire, for this will be an easy topic to get through. And then galactic radio emissions. So let's start out with the electromagnetic spectrum. Claire again highlighted on this. We're going to start in the center. This is our visible light. This is what we all use with our telescopes. We see with our eyes. And if we want to go higher in frequency, we go to ultraviolet, X-ray, and gamma rays. And then starting at the middle again, visible, we go the other way, infrared, microwave, and down to radio. And we're going to be talking about radio this section tonight. So this is another graphic of the spectrum. And again, we start with visible in the middle. And as we go higher towards ultraviolet, X-ray, and gamma, we have short wavelength, higher energy, and higher frequency. Again, start from the middle and go the other way. We have infrared, microwave, and radio has longer wavelength, longer energy, and longer frequency. So let's just look at the radio spectrum in a big chunk here. So this is the chunk of the radio spectrum. It starts out with very low frequency, then it goes low frequency, medium frequency, high frequency, which is the shortwave radio band. And this is what we're going to be talking about tonight, and specifically 20 megahertz or 15 meter for you hams. VHF, UHF, super high frequency, and extra high frequency. Anyway, VHF and UHF, does that sound familiar to people? Long time ago, we used to have something like this on our TV set. And it was a set of what we called rabbit ears. If you remember that, And in the center, you had this little loop antenna. Well, the loop antenna was for the UHF, the higher frequency, so it was a smaller antenna. If you went down to VHF, which is bigger wavelength, you needed the big rabbit ears. So two types of antennas for two different frequencies, VHF and UHF, back in the day of television. So antenna does mean a lot when you want to receive a specific signal. All right, so just another graphic real quick, visible light in the middle, and the frequency is about 100 terahertz in the middle of the visible spectrum. That goes down to about 10 terahertz. Then when you get into infrared, down to 1 terahertz. You get into microwave and the radio spectrum, you're down to the gigahertz range. When you get down to the upper UHF, it gets into megahertz, and then it goes down to high frequency, where we're going to be talking around 20 megahertz. But it keeps going lower, down to 100 kilohertz. Then it goes all the way down to hertz. So these are wavelengths. And again, I said I'm going to be talking around this section, the upper band of the high frequency band, but just under the VHF band at 20 megahertz. So I've been talking about 20 megahertz and wavelength. 20 megahertz. How big is a wavelength at 20 megahertz? Well, let's put up the spectrum again. Very easy graphic. We're going to start in the middle with the visible here. And if we go up to ultraviolet, X-ray, and gamma, the size of a wavelength up at the gamma ray is about the size of an atomic nuclei. X-ray is about an atom. Ultraviolet is the water molecule. The visible light that we see through our telescopes and all, those wavelengths are about the size of a virus or a bacteria. They're small. They got to get through your iris of your eye so your eye can see the wavelengths. And like the antennas, it's got to make it to where it's going to pick up that frequency. Then you get down to infrared, gets the size of a pin, microwaves, a penny, and you get down into the radio waves where we're talking about. These wavelengths could be anywhere from the size of a human being to a football field. So I keep using that word wavelength. What does that mean? Well, this is a sine wave, electromagnetic sine wave, a wavelength. And the wavelength is from one crest to the next crest. So that is the size of a wavelength. Well, size of a 20 megahertz wavelength. What's that size? Well, there's a formula for that. It's wavelength equals the speed of light, which is V, divided by the frequency. So we all know the speed of light, 186,000 miles a second. And if we convert that to metric to make the math easier, oops, I'm pushing the wrong button. It is the 3 times 10 to the 8th power meters per second over 20.1. And we're going to be talking about 20.1 megahertz times 10 to the 6 hertz equals 14.925 meters. For you people that can't convert from metric to feet, that is equal to, this moving forward. Okay, it's just stuck in some mode here. Try it. There, okay. So how much is 14.925 meters? It's 48.8 feet for one wavelength. So one wavelength, oops, wrong way, 48.8 feet. That's a big wavelength. Brian, raise your hand. From there, all the way over to this bottle on the table is one wavelength at 20 megahertz. That's big. So we're talking size when you want to talk about a backyard radio telescope at 20 megahertz. So here we're back here again, the spectrum. So oops, we're going to be down here 48.8 feet, bigger than a human, not quite as big as a football field. So moving on, let's get on now to Jupiter emissions. I just gave you a rough idea about wavelength, the electromagnetic spectrum and all that. So this is really what we're going to learn about with our radio telescope tonight is Jupiter emissions. So I mentioned 20 megahertz. Why 20 megahertz? Because of Jupiter. Because radio Jupiter emissions were discovered accidentally in 1955 by Burke and Franklin using an antenna array in Maryland. They were observing the Crab Nebula at low frequencies, 22 megahertz, but they also observed what they thought was local interference. On further observations, and this is over months, they confirmed that the source of the interference must be Jupiter, and they made their announcement to the American Society, Astronomical Society. There's a roadside plaque there today. So if you went down there, I'm not clicking again for some reason. Right now. There it goes. So this is Washington, DC. Up here in the upper right is Baltimore. So if you go to Washington and you follow the Potomac up, there's a farm field, and this is where their antenna array used to be. This is a picture of the antenna array that they used to discover these emissions from Jupiter. And if you look at these pictures, look at this pole here. And there's a wire going across to the next pole, and there's a wire dropping down in the middle. This wire dropping down is the middle of another wire that's off the picture. That's a classic dipole, and that's what we're going to be learning about tonight. This is going to be your radio telescope, exactly what they used. And this antenna array consisted of 66 unpainted poles, which is 33 dipoles, all the way down the line there. If you go there today, there is a plaque out by the road. It says planetary radio emissions. And halfway down in the paragraph here, it says accidentally discovered naturally generated radio waves from Jupiter using a 96-acre antenna array. Now, you're driving down this road at 45 miles an hour and you look at this plaque, planetary radio emissions. You're going to think Saturn, Mars, Mercury. I really wish they put Jupiter radio emissions on this plaque, but they didn't ask me, and I was only 1 year old when this plaque went up. So no, that's the way it goes. So this is their data sheet, not a spectrograph, a graph of their data. This is the Crab Nebula, and they have over here in the upper right, January 25th, 1955. Then they took another reading on February 11th, February 15th, February 24th, and February 27th. And there's the glitch on the strip chart recorder, and that's the Crab Nebula. But look on the other side. Wow. They looked at something that said this had to be local. This no way that they would have thought this came from their solar system. But after months of observation, a lot of studying, they have determined that Jupiter is emitting these emissions. So Jupiter emits two types of radio emissions. Io-related emissions is one. Io is Jupiter's closest moon. It's the most active volcanic moon in the solar system. Sulfuric dioxide being thrown up above the surface. And because of Jupiter's high magnetic fields, the atoms or the electrons in the sulfur gets ripped apart, and you have a lot of free electrons floating around Io and around Jupiter. The next type of emission is non-Io related, meaning the moon Io has nothing to do with the emissions. It's only Jupiter. So Jupiter, we're going to talk about the non-Io related emissions first. This is a graphic of Jupiter looking down on its rotation, rotates 10 hours, and there was 3 anomalies discovered on Jupiter, and they labeled them A, B, and C. These are not surface anomalies. These are not like the Great Red Spot or cloud bands. These are way down inside Jupiter towards its core. And this graphic here will show Earth is looking at this anomaly. They call it a CML. A CML is the longitude of Jupiter that's facing the Earth. So Jupiter's radio emission probability of occurrence has been mapped over many years of observations. 3 main sources have been found and are labeled A, B, and C in Jupiter's longitude system. The central meridian longitude, CML, is defined to be the longitude of Jupiter that is facing the observer based on a fixed rotation period. So if we look in this white graph here, we can see the anomaly, the magnetic anomaly, electromagnetic anomaly. B is around 150 degrees, A is about 230, and C is about 330. So this chart up here on the right shows you the probability. Now, these three anomalies, A, B, and C, are not constantly broadcasting electromagnetic waves. They get strong. It's kind of like Old Faithful geyser or something like that. They go strong over a time, then they go real weak. So this map shows you the probability, and A is obviously the strongest, and B and C are about the same. If you go online and look more into this, again, I'm skimming the surface. These would be called non-IOA, non-IOB, and non-IOC. These three anomalies, because IO has nothing to do with these emissions. This chart, the CML, is actually called a system 3, what they use, is associated with the emission. It's radio telescopes that astronomers determine Jupiter's rotation. They observe the rotation of the magnetic sphere, which is believed to be connected to the solid core of Jupiter. Then there's a system 1 longitude. Like I said, if you see something that says 230 degrees, it's a system 1. Well, they were using an equatorial zone system. But if you see something that says 230 degrees using the system 3, they were using the magnetic, one of those three magnetic anomalies on Jupiter. So the chart below has non-IOA, non-IOB, non-IOC. This is the CML range of those anomalies. IO range is 0 to 360 degrees. In other words, IO has nothing to do with these emissions. The maximum frequency, 38 megahertz on B and A, 32 on C. The Voyager spacecraft found IOB and non-IOC, non-IOB, but we found IOA from Earth-based observations before the Voyager craft discovered the other two anomalies. So to look at a graphic of what I'm talking about here, Jupiter, this is Jupiter. These are those very strong magnetic lines of force. I guess you could say they're like the Van Allen belts on Earth, but these are very, very strong. And this is Io in its orbit around Jupiter. And remember I said about those electrons being ripped from the sulfur atoms? There are a bunch of free electrons. It creates a plasma torus in orbit around Jupiter. Io rotates around Jupiter, and depending on how it lines up with these anomalies, not necessarily the A, B, and C, but just any magnetic field, it creates a flux tube of electrons. It's like a short circuit, a spark, crack, and that short circuit emits the radio emission that we can pick up. Here's like a drawing of what I'm trying to say, and this is the plasma torus going around Jupiter. This is Io with its flux tube, and this is the current that occurs when Io gets into a certain position and creates that short circuit. There's a lot of dynamics that goes on in here. You can do a deep dive in this, but again, I'm just skimming the surface. But it's not that easy. When this short circuit occurs, it's not like the towers down on Domino Lane that just broadcast out everywhere. Life should be so simple. This is graphic. This is Jupiter with its magnetic field. This is Io. When that short circuit occurs, it creates a cone, an area that broadcasts that short circuit. And if Earth was over here on the right, you're not going to hear anything. Earth has to be in line with that cone. But it's not, it gets a little bit more complicated than that because there are a lot of cones on the north and south, depending on IOC, IOA, IOB, non-IOA, and it all depends on where you're oriented. This is a lot of dynamics that go on here to catch one of these signals or these emissions that Jupiter emits. These spectrographs here are some pictures, and if you notice, IOB is the strongest. Then a spectrograph, IOA here, the colors are light blue, but as the signal gets stronger, it gets yellow, and if it gets really strong, it goes to red. So you know there's yellow in here, that's a real strong signal. And I'll tell you right now, if something you're going to pick up when you leave tonight is if you want to try to listen to Jupiter, you want to try listening to IOB as you're listening, because that has the highest probability, it's the strongest signal, and it's the one you really want to get your feet wet with. So that is pretty much how these emissions work on Jupiter. So solar flares, Claire did a lot. Thank you, Claire, on explaining this. Solar flares, can cause emissions at 20 megahertz range. The emissions, when observed as type 2 or type 3 bursts, are generated by the acceleration of electrons during a solar flare and their interaction with the sun's magnetic field and plasma. The burst can be strong enough to cause radio blackouts at these frequencies by increasing the ionization of Earth's atmosphere that Claire alluded to. So the ionization of the ionosphere is a very important part if you're going to be listening to anything from Jupiter. And we know these flares are strong. And if Earth is in line with one of these, yeah, we're going to get a good aurora. We're going to get a lot of interference with our radio. If these flares are on the other side of the sun, yeah, you're not going to see nothing. So you really have to be in line with the Jupiter emissions, along with solar flare emissions. All right, so moving along here, galactic radio emissions. I'm just going to skim over this. This is a graphic of our galaxy looking down. The center of our galaxy's in the center here, and we're out here on the local arm. And between us and the center of the galaxy is the Sagittarius arm. We can't see the center of the galaxy because of all the stuff in the arms that are between us and the center of the galaxy. But radio telescopes have picked up the center of our galaxy with some really neat stuff going on. And these radio telescopes are the big ones, and they're up in the gigahertz range, not down in the 20 megahertz range of our backyard radio telescope. These are the big boys. And they picked up, this is up here in the upper right, is over the years, these radio telescopes follow these stars, and they're obviously going around something in the center, something very powerful. I call it the monster in the center of the galaxy. It is the black hole. You just can't see it, but it does create, I shouldn't say it creates, it does disturb a lot of stuff in the center of the galaxy. The event horizon creates a lot of X-rays, a lot of junk. But anyway, so that's what's happening at the center of our galaxy. So we talked enough about theory. You get a rough idea of wavelength, how big the wavelengths are, 20 megahertz, and all that stuff. Let's talk about the construction now of our radio telescope. So what got me started in this? Astronomy magazine, 1977. There was a 6-page article in the magazine that just won my heart. I don't know how else you could say it. And in the article, they chose a cubical quad as the antenna. You ham radio operators know a cubical quad. That's the old shortwave World War II, radio. It's very efficient, but it's a big antenna. As you can see from this picture down here, it's large. It's huge. I didn't have a large backyard at the time. So instead of a cubical quad, a couple of years later in 1980, I built my first Jupiter radio telescope. Believe it or not, that's me. Piece of plywood, window screening on the plywood, and aluminum tubing for the antenna. And if I look at these sizes of that looks like about a quarter wavelength of 20 megahertz. It's about the size. And that's here. I don't know where I got this data from. I don't know how I found this construction, but for my little backyard, it worked. But it didn't work very well. I picked up a lot of noise. And back in 1980, there was no computers or nothing like we have today. I had a mechanical strip chart recorder and a shortwave radio with a headset on, and I listened to Jupiter. I thought I was listening to Jupiter. I really wasn't. I probably was listening to my neighbor's 1969 Chevy that he backed down his driveway or drove up and down the street. I was picking up a lot of noise. I really couldn't discern if I was listening to Jupiter or not. So move forward. Life went on, moved to another house, had kids, raised them and all, had a big backyard. I said, I really want to build this cubical quad. Well, there's the cubical quad in my yard in 2002. It's huge. Each length here is 48 feet, the wavelength of a 20 megahertz. And it's all wood constructed. So I painted it. I put Thompson water seal on it. And this is when I did the talk at the Schuylkill Valley Nature Center for the DVAA, once I built this. And then I went and somebody asked me to do the talk at the local ham radio club in Malvern here somewhere. And the Inquirer got a hold of it, and they came up and they did a little article on me. The pictures in front of me of the radio telescope didn't work out, so he wanted to take a picture of me in my observatory. And he put Don McLaren has a love affair with Jupiter. I wish he could have wrote something else, but I was still humbled that this article was in the Enquirer in 2003. So anyway, there's my cubicle quad. It was all wood and it lasted for about 15 years. I would come out in the wintertime with a broomstick and bang the bottom of the lobes to get the snow off it. I was treating it like my little pet in the yard. And it just kept deteriorating. And every now and then a deer would come through the yard with his antlers and catch it on the bottom of the antenna. It was just brutal. So it didn't last. It started to fall apart. So in 2017, I changed the antenna to a Yagi. It's a 15 meter. And for you ham radio operators, this was bought from a ham radio shop down here in Delaware. And it was a kit cut to the length of the wire. Everything's cut to 20 megahertz. And I think the way this works is this is the receiving, the back's the reflector, and the coax cable is connected to the center one. So it was very directional though. You know, if you were trying to do the sun, you had to have that point, and soon when the sun came in front, you maybe got some noise from the sun, and soon it left, you didn't get nothing. I mean, it was very directional, it steers, but it was a good antenna. Well, this is the picture of my yard today, and this is my Yagi antenna. This is my observatory. I built this in 1990. It's kind of a little campus here with the gazebo. I have a Hoya pond, a little bridge, and I used to have a pool in the backyard, that above ground pool, but once the kids got old, moved out, it was a big open lot. And you really can't see it good with the trees here. But then there's my dipole, dual dipole antennas in the back. So I have my Yagi antenna, my dual dipole antennas. People come and look in the observatory, they say, oh, yeah, there's my telescope. And I take them out and say, these are my other telescopes. You're looking at the same thing, only a different wavelength. It's the same thing, electromagnetic energy from visible light to 20 megahertz. It's the same thing, just a bigger wavelength. All right, so let's move on here. Let's build the radio telescope. So get your neighbors together, get some money together, and we can do this. All right, let's build it. We got a big backyard. Come on. There's the enthusiasm in everybody here. Well, truthfully, what we're going to be building, a dipole that I showed you. No, not the TV set, but the rabbit ears on top is the dipole. It's the perfect antenna for a backyard radio telescope. Look at this TV. Remember VHF and UHF that I explained? Two different tuners. That was the age. It was amazing. So let's talk about a dipole. The dipole is the simplest antenna. Is a dipole which can be made from two pieces of wire. Quarter wavelength on each side. You have your feed point in the middle and your coax cable going down. So much like, this is important, much like a pipe organ is cut to a specific length to make it resonate for a particular frequency of sound, our dipole antenna is cut to the length of half a wavelength to make it resonate at 20 megahertz. So how big do we make this dipole? There's a little math formula for that too. The formula is for length of a half a dipole in feet on the left side and meters on the right side. So it's 2 divided by the wavelength equals 468 by the frequency of 20 megahertz. What the hell's 468? I couldn't figure out where that number came from. Well, the number 468 is a constant. It's one of those magical numbers used to approximate the length of a half-wave dipole, accounting for the velocity factor in a wire. We'll learn about the velocity factor in a little bit. So if you cut the dipole cut to 20.1 megahertz has a length of 23.28 feet, or 23 feet, 3 inches is measured from tip to tip. So there's your dipole. 23.28 feet, each side quarter wavelength, 11.64 inches. And there's your feed point and your coax going to your receiver. The feed point, okay, you built your dipole or you got the wire length. The feed point, very simple to build. It's a ceramic insulator that you can get online, Amazon, you get a bag of them for like 15 bucks. And one side of the dipole is connected on the one side with solder, and this is the other side of the dipole. You have your coax cable coming up, wrapped around with a tie wrap for strength, because remember that old picture I showed you in 1955, the dipole with the wire coming down in the middle? Well, that's where you need a little engineering support for your coax hanging down. And coming out of the coax, there's two wires, there's the shield and the center line. They both, each one goes to each side of the dipole. Very simple. This is another coax cable, same configuration. The shield goes to one side of the dipole, the center wire goes to the other side of the dipole. This is a cross section of a coax cable. You have your center lead wire with an insulator and your shielding. Sometimes the shielding can have aluminum in it. Sometimes the shielding is made of aluminum. I, tried to solder, and solder won't solder aluminum. But I like to go with copper when I'm using a coax cable. So let's talk about okay, you got your dipole, you got your feed point all made. Let's talk about antenna height. So at lower heights, the beam pattern, which we're going to talk about beam patterns here in a minute, is less focused and radiates the signal upwards. As the antenna height increases, the beam pattern focuses more towards the horizon, improving long distance communication. So let's look at Jupiter with elevation. This is Jupiter's declination here over the next many years, and the bottom is its elevation. So if we look at the declination, the top chart, 2025, the declination of Jupiter is about 22, 23, plus 22 or 23 degrees declination for 2025. We look at the lower chart, the green line is us at 40 degrees latitude. So if we look at the top of the green line, our elevation above the horizon for Jupiter right now, 2025, is about 73 degrees above the horizon. But look what happens. 2026, we're still okay, but 2027, 28, 29, when you get down to 30, the elevation of Jupiter is going to be below 30 degrees above the horizon. That's very low. So you got your dipole in your backyard. Jupiter's very low. What do? Well, we're going to look at these antenna patterns. But again, this is just a graphic. I don't do a deep dive into this. Don't want to make it look too confusing. But a single dipole, 10 feet above the ground, has a gain of 5.8 decibels. Don't worry about decibels. Just know the number, 5.8. And its elevation is 90 degrees. So it's straight up. But look what happens when we play with the height. So this is the graph of Jupiter again, and Jupiter's going to be dipping down to 2030 here. This is the graph I just showed, a dipole 10 feet above the ground has the gain with the elevation straight up. But look what happens when we raise the dipole up to 15 feet. The lobe flattens out. Your gain's about the same, but now your center point, your sensitivity is now over here at 48 degrees. So by raising the dipole, you actually made the antenna point a little more down towards the horizon. If we do the single dipole up to 20 feet, this lobe really flattens out. Look at the gain does increase, but look at the sensitivity of the lobe. It's down to 34 degrees. Now, this is the south lobe, or south. This is north. And this is going to have the same sensitivity north as the south area of your dipole. But we don't care about the north because the ecliptic is on the south. The sun and Jupiter follows the ecliptic. So we're only concerned with the south. So raising this dipole does affect the elevation of your antenna. Oop. Oh boy. I'm jumping all over. Okay. Did I do this? Sorry. All right. So the cable running from the feed point of your dipole or the power combiner, we'll be talking about that in a little bit, to the receiver should be in multiples of half a wavelength. Remember, like the pipe organ, it's got to resonate. So the feed point or the power combiner to the receiver would normally be half a wavelength or 23.28 feet. The magic number divided by 20.1 megahertz is 23.28 feet. But there's always a but. Nothing's easy in life. There is something called the velocity factor. nothing overcomplicated, but the velocity factor in a coaxial cable represents how the speed of an electrical signal is reduced compared to the speed in the vacuum. So let's bring in the math again. Sorry, but you're really going to need some of these. If we use the coaxial cable RG59U, its velocity factor, again, a magic number is 0.66. This is going to be on the test. And if you don't get it right, nobody leaves here. These are test questions. These are just magic numbers to know. So 0.66. So if you remember that old formula, wavelength equals speed of light divided by frequency. So if we do the formula to the effective wavelength, which is the velocity factor built into the cable, you have the wavelength of the velocity factor, or the effective wavelength is equal to the velocity factor times the speed of light divided by the frequency. Plug in your numbers here and you get 9.85 meters or 32.28 feet. That is for an RG59U cable. Used to be able to get that at Radio Shack. You can get it online. My yard has the RG59U, but there is a cable of RG6U. You can get this in Home Depot. It's more readily available, but its velocity factor is 0.78, that magic number. Plug all the numbers in again, and you get 11.64 meters or 38.19 feet. Look at the difference, 32 to 38 feet, just using a different coax cable. It's very important to do these numbers depending on the cable that you have. This chart, let's just look at the one cable length in wavelengths. One wavelength is 32.32 feet for an RG59U. It has an attenuation of 0.5 dB. Again, don't worry about that number. This is kind of like a signal loss. All you just need to know is it's 0.5 for an RG59U. But an RG6U, the kind you get at Home Depot, the cable length is 38.19. It's a longer cable, but look at this. It has a less loss in it, 0.32 dB. So that's the magic of radio. I don't want to get into the physics of all this. I'm just skimming the surface here. But RG6 is a thicker cable than RG59U. Again, I don't want to get into the mechanics of all this. I'm just skimming the surface. Okay, so there is a movie that I love, Contact, with Jodie Foster, and everybody's seen that movie. And there is a scene in that movie where she is talking to the rich guy in orbit. And the thing that they downloaded, remember, it was destroyed and she's all bummed out. And she's talking to this guy in orbit who is funding the project. And he says this. Let's do that again. Wait a minute. That's it. Why have one when you could have two for twice the price? Build two dipoles in your yard. Oops, wait a minute. Oh, geez, sorry. Button nuts here. So you have a north dipole and a south dipole. You have your feed points that we already talked about. Your coax cable now goes to a power combiner out to the receiver. And remember, these dipoles are east to west. And said you have a north dipole and a south dipole. This is an aerial view looking down on the two dipoles. We already know the length of these dipoles, 20. This is an approximate, it says approximate 25 feet, but we already know it's 23 point some feet if you did the math. And the two dipoles apart are just about a wavelength too. So you're going to have these almost at 23 feet apart. This is all the mechanics for people that don't know how to pitch a tent, you know, how much feet of wire and all that stuff. I used to use on my first dipole a tree, and I screwed an eye bolt into it, and on the end, oops, nuts. Keep doing that. And on the end of the dipole is a rope, and I put it through the eye bolt on the tree, and I hung a brick under it. And on the other side of the dipole, I did the same thing on another tree, put the rope through an eye hook and hung a brick. And as the tree swayed, the bricks went up and down, but my dipole stayed pretty taut. Mechanical engineering, that's all it is. So anyway, that's an overall view of the dipole. But remember, on a single dipole, the height above the ground affects the antenna beam steering. But on a dual dipole, Steering is done by a phasing cable. All right, what do we mean by phasing cable? Well, on your dual dipole, your north and south dipole, on the south dipole only, you put in this little extra cable length here. And I don't want to get too much deep into this, but it's called a 90-degree phasing cable. It's 8.33 of extra coax cable that you put into this little phasing, in this little section of the south dipole before the power combiner. The 135-degree phasing cable is 12.12 feet of coax cable. So what am I talking about here with phasing cable and affecting this on the south dipole? On this diagram here on the left, you're looking at the two dipoles. Like if you're standing west looking east, so you're just looking at the wires, your signal's coming down, hitting the both dipoles, they hit the combiner and they're amplified. But on the right diagram, small d is the phasing cable. That little extra bit of cable on the south dipole is a little extra length for the signal to travel. So essentially, that makes the signal coming in, and this is only a graphic here, that it's going to hit, the signals are going to say it's going to hit the south dipole first, and it's going to travel a little bit more distance, big D, to hit the north dipole. So essentially, you steered your dipole. Beam steering. By introducing this phase shift into the south dipole, the antenna array becomes more sensitive to radio waves arriving from the south, effectively steering the antenna beam towards that direction. So let's look at some examples on these beam patterns that I showed earlier. All right, this is the beam pattern that we already looked about. It's the single dipole, 10 feet above the ground, has the same, there's your, dB, your degrees is straight up. But now look at this, the dual dipole, same 10 feet above the ground, no phasing cable. It's got a little bit more gain, but look at your beam pattern compared to the left, one on the left and one on the right. It's narrower. That's where you get your little bit of a higher gain. So again, why have one when you can have pay the price for two of them? You get a better gain for sensitivity of these Jupiter emissions. If your dipole now has that 90-degree phasing cable in it, which was 8 feet some inches, look what happens to the beam pattern. It now comes down to 60 degrees and your gain goes up. This is the magic of radio. I don't want to get too much into this. This is just graphics to show you. But if we look at, now this is a misprint, it should be 10 feet here, but your dual dipole 10 feet with the 135-degree phasing cable, that's at 12 foot of extra cable on the south dipole, gives you a nice gain of 9.5 decibels. But look at the elevation. It's all the way down to 33 degrees. So when Jupiter in 2030 becomes real low from those earlier graphs you saw, this phasing cable is going to come in handy if you have a dual dipole to pick up Jupiter. So we talked about the dipoles, your feed point. We talked about the phasing cable. Now your coax cable going to the receiver. This is important. The cable running from the feed point of the single dipole or the power combiner, the dual dipole, to the receiver should be in multiples of half a wavelength. Remember, it's like the pipe organ. It's got to resonate. All right, so we covered theory, covered construction. Let's talk about operation. I can get this to go. There it goes. So let's talk about operation. All right, so when you get into this, if you want to dabble into this world of a backyard radio telescope, a dipole, you are going to definitely need an app that's online. So this is the Jupiter Prediction Storm. You get it at radiosky.com. The guy that wrote this app way back in the 90s, his name is Jim Sky, believe it or not. I don't know if it's a Hollywood name, his last name's Sky, but he wrote this software. Unfortunately, it's for Windows only. I asked Jim if he could write it for Android, and he said, Don, I just don't have the time. I got to rewrite the code and all. Maybe, but it's not on my bucket list. So you really need Windows to run this. This app is free online, but it's got limited capabilities on free, but it will give you the predictions. But this is the main screen of the app on the left side. It's called the Radio Jupiter Pro. And again, you just can Google that and you download this app. The app costs about $10, $15, it's cheap. But if you click on the display portion of the main screen, it'll have a drop down, it'll give you radio Jupiter noise storm predictions. This is a nice graphic. So I put today's date in, 8/8/2025. This top green line is Greenwich Mean Time. The bottom line in gray is local time. And the color bars on the left is your A, IOA, B, IOB, C, IOC. We already know A, B, and C are non-IOA, non-IOB, non-IOC. And then you have IOB, IO, and IOC. So remember I said about IOB being the strongest. So if you have this app, this color is really what you want to go for, this light blue. And we can see tonight, wow, there's going to be an IO storm prediction. And it's going to be between midnight and just before 2 a.m. Well, if you look at this bottom part, it says blue background indicates Jupiter's below the horizon. So no IOB tonight. But here at 2 in the morning, you can see it goes yellow. That means Jupiter rises above the horizon and it's up and it doesn't set till around 5 o'clock in the evening, 1700, our time here. And you do have a non-IOC and you have a non-IOB and another non-IOC and you have a non-IOA. These are real subtle storms, but look at the graph underneath the main graph. It's the sun when the sun rises. So it comes up around 5 a.m. It doesn't set to around 6. I don't know if I incorporated daylight savings time into this when I did this or not. But anyway, when the sun's up, forget about trying to get IOB unless you're very good with tuning your telescope and no noise. It ain't going to work tonight for tonight. But this app is great. You just really need this app if you want to start maybe trying to listen to Jupiter. So let's put this all together a little bit here, and I'm going to show you one other thing you're going to need. So this is your dual dipoles. There's your feed lines going to your power combiner and the lead going in. This is the box that Radio Jove, which is called today, uses. It's called the SDR Play Software Defined Radio. This box came out about 10 years ago, and the Radio Jove program uses this model, the RSP1, but now it's B. You can't get A anymore. They upgraded it. So you have your radio telescope going into this box. This box has a USB port, goes to your laptop, and you are running a spectrograph. And the spectrograph is written by Jim Sky from radiosky.com. It's, again, another cheap app, free for limited use, but I think $10 or $15. It's not expensive to get the spectrograph on your laptop. All right. This is the receiver that Radio Joe Project used back when I had my cubicle quad. It is the Radio Joe receiver. It's only 20 megahertz, and you can buy it assembled or with a kit. So I bought it assembled. It's a simple box. The back of the box has your antenna input, and then there's your 2 audio outputs and your 12-volt input. So remember, back in 2003, my computer was those tower computers. Remember the sound cards you used to be able to plug in and all the optional cards? I had a sound card. So the audio out went to the sound card, an A to D converter, analog to digital, and it was able to produce a spectrograph on my computer. But today it's been replaced by the RSP1B. But look at that range, 1 kilohertz to 2 gigahertz. You're only going to use 20 megahertz for this box for Jupiter, but you can have fun with it. At that span, you can listen to marine radio, you can listen to police radio, airports. You can have a lot of fun with this box. There's a lot to do, but the back of the box is just as simple, the RF in and your USB out. And that's another picture of it. Now this RF in is a small connector. So if you go to Home Depot and buy that RG6U, it's going to be the connector that's like on your Comcast cable that you plug into your box at home. It's about that size. This is smaller, so you need a little converter. And then there is the USB cable going out to your computer. So here's your setup. You have your cable coming in, your little converter that goes to your SDR Play box, The USB port goes to your laptop. You're running your spectrograph. The bottom graph here, the bottom block is another little thing you're going to need. So you got your dual dipole, you got your SDR play radio, and you have your Radio Sky spectrograph software running on your computer. To make the SDR radio box talk to the Sky spectrograph, you need this app. It's called SDR Play to RS or RSS. That's the SDR Play box to the Radio Sky spectrograph. It's just what it's saying is what it does. This was written by Nathan Town, and again, he matched the box up with Jim Sky's spectrograph. And this is a close-up of that app. When I got it, all I did is plugged in the numbers. I got a picture online and plugged in the same numbers. If you click on integrate and it goes yellow, your telescope is live and you are recording. One time I put here in the offset 1.0, and I kept clicking integrate and it wouldn't go yellow, and it took me a while to figure it out. And this example I used online, 27 megahertz is your center frequency. You want it to be 20 megahertz. And again, all these little things, you can tweak them a little bit depending on how much noise you have in your backyard. You have the transformer on the telephone pole. Do you have your neighbor with that 1969 Chevy across the street? Depends. But this is the spectrograph here, a picture of it. These lines is all noise. This looks like a radio station. And down here below 18 megahertz is a Spanish radio station. Comes up on every spectrograph. But see this little hazy, fuzzy stuff? That's Jupiter. That's IOA. So you'll get to know this as you get a little more experienced with the spectrographs. This is a close-up of the spectrograph. And again, notice your 20 megahertz is centered in between the 8 megahertz bandwidth. This is all noise. And WWV still broadcasts its time and frequency information 24 hours per day, 7 days per week at 20 megahertz. If I look here, I really can't see it. This is not WWV because it's too far above 20 megahertz. I think this little bit here might be WWV. Depends on your location. And I think this graph was the guy in South Carolina. So location means everything for your spectrographs. This is a close-up again of that app that you need to connect the SDR play box with the spectrograph on your laptop. Okay, so now we're at the block diagram. So you got your single or dual dipole going to your SDR play box. Now you have the app to connect the SDR play to the Radio Sky spectrograph. And there's your setup. And then you always have the little Radio Jupiter Pro software to know when that storm from Jupiter will happen. The websites to get these from. Websites, you just Google Radio Jove, NASA, you'll come up with this very easily, and the software from Radio Sky. But NASA, the Radio Jove NASA site sells kits. Button nuts here. The kits are kind of expensive, $220 for the kit they send you. If you want the antenna all assembled for you, $384. I mean, that's for people with deep pockets. And if you don't have poles, they'll send you them for another $150. What I suggest is that you just get the SPR or the RSP1B box. This costs about $130, and you can get this online, or you can get it from a website that I'm going to show you in a minute. But get that model, RSP1B. The ham radio shop in Delaware sells them. And all the rest of the stuff, you can piecemeal it. Get your ceramic insulators online, get your cables from Home Depot, your wire, and the instruction manual is online. It can be downloaded free. You just Google Radio Jove. I'm stuck again. Oh, there it goes. That's the thing. These are some observation examples of spectrographs. Now, look at the one in the lower right here. These are solar bursts, and they're always going to be vertical in the spectrograph. And you can see the light colored here and light blue. these sidelines are radar sweepers. So depending on your location, if you have a weather station or an airport nearby, you're gonna see some interference. These long horizontal lines are radio stations. There's the Spanish station down here. It's always on every spectrograph. But look at the one in the upper left. These are solar bursts, and you can tell how intense they are because they went from light blue, yellow to red. So it could have been an X flare. And it's live. I mean, you're seeing this as it happens. This is a Jupiter burst, and it's subtle. It looks like a little waterfall. And these lines in it are giving an indication that it's modulated. I don't want to get into that now. You'll learn more about that. But that's a Jupiter burst. These are solar bursts. And this is terrestrial propagation. You're going to get to know that through experience of looking at these graphs. Now, what I recommend highly, if you want to get your feet wet into this, there's people all over the United States that have these radio telescopes up, down in Mexico, South America, up in Canada. Get on this email list, groups.io/g/Radio Jove. You will get on their list. Every day you'll get emails from these people showing you their spectrographs. Hey, I got IOB, or hey, I got these solar flares. And you, over time, you look at them and you can delete them, but you'll get to know the patterns. You'll get to know a lot about this type of hobby. Larry Todd, another great guy, he puts his spectrograph on YouTube every day live. And here's a solar flare that looks like an X flare. And he puts over here on the side Jupiter from that Jupiter Pro predictions software. He puts that on the side here, and there's little dynamics in here. I want to get into explaining all this, but it'll tell you by looking at the graph if the planet Io or the moon Io is over one of these spots, so you're going to have an IOB storm. And the top little one shows the sun with Jupiter, you know, if they're together, if they're separated. Remember I said you can't get IOB during the day. It's really hard because of the ionosphere. It gets all heated up and it's hard to get those weak signals to come through. So this is the old way, the strip chart recorder that you can get from Jim Sky's site. I like the strip chart recorder. I'm an analytical guy. I'm an oscilloscope guy. I like the strip chart recorder, but below is the exact signal on the spectrograph. So if you look at the strip chart recorder, like in the center, this peak goes off the chart. So you know it's strong, but when you look at the spectrograph, it's yellow, so you really know it's strong. And this is a solar flare, and this is probably the Spanish channel. All right, so if you go to that NASA site, you will see that they sell these kits. Oh, come on. There it goes. They sell these kits, and they're quite pricey, again, for deep pockets. But all I recommend that you do is piecemeal it. Just buy your RSP1B box, and gather all this stuff that you can, download the box, and then you can have your backyard radio telescope.
Use the right arrow on.
Yeah, I'm using the down arrow, right? Yeah. All right, so these are some Jupiter Io storms viewed on the spectrograph. This is an IOB. It's nice and subtle like that. You can tell this is an IOA. They are subtle like that. This is solar flares, and they're all vertical. There's a light one, there's a stronger one. And again, from color alone, this is a neat new way spectrographs work. You can tell how strong that solar burst is. This might have been the next flare, and it goes pink like this. The timestamp on the bottom, this all records. Your 20 megahertz is in the center. Spectrograph is a really neat way of looking. So remember earlier I mentioned about the galaxy and the energy in the center of the galaxy. Well, this is a thing I did a couple of years ago. Here's my two graphs, 24-hour graphs as part of my radio telescope done on separate nights that show, wow, that was magic. I was using the pointer. Did I go back?
Radio.
I don't know what happened there.
Oh, maybe click on maybe that. There you go. Let's try that again. So anyway, done on separate nights to show the intense radio source at the center of our galaxy in the constellation Sagittarius as it passed through in the south through my antenna beam. The passage occurs around 4:30 in the morning. Remember, when the ionosphere is quieted down correcting for daylight saving time when the radio sky is at its quietest compared to the daytime noise. So you look at these two graphs, started in the morning, here's the noise from the sun, look at the noise, but then you let the spectrograph grow, and there's this little hump in the middle around 4 o'clock in the morning, then the sun starts to rise, there's a noise again. A couple days later, I did the same thing, different noise, because you get different ionosphere conditions and all that, but you still got the noise from the sun, let it go through the night, then around 4 in the morning, you had that little bump, and then the sun comes up. So I call these things that go bump in the night. It doesn't give you much data. It's just more like a fun experiment to catch like, hey, I got these signals from the center of the galaxy. So Jupiter storm sounds. All right. So we talked about the type IOB, non-IOA and all. So you're going to listen to IOB. IOB is mostly going to emit the type of short bursts. So there are long bursts that sound like waves breaking on the beach, short bursts that sound like pebbles dropping on a roof. So let's listen to an IO, or not an IO, an L burst from Jupiter. You close your eyes, it sounds like waves crashing on the beach. Okay, now let's listen to short bursts. Little pebbles dropping on the roof. This is the more popular sound that you will hear if you want to dabble into Radio Jupiter. You will get short bursts. This was my first radio signal that I heard when I had my people to fly. Bursts only last for a couple minutes. You use that app, it'll tell you when the storm will occur, will really help you. So we went through a lot tonight, we showed you a lot of things, but let's make it simple. You have your shortwave radio at home, you have your single dipole in the yard, you run your coax to your radio. This antenna will not pick up radio signals from Jupiter. You'll pick up a lot of noise. You'll pick up that Chevy in the backyard, but you're not going to pick up Jupiter at all. You need your dipole cut to the right lengths in the backyard and hook to this radio. This shortwave radio better have AGC where you can turn off automatic gain control. You need to turn that off. And you can either crank up the speaker when there's a short burst of Jupiter storm predicted, or you can put it through your headset on listen through the headset. So make it simple, get your feet wet into this, and then as you slowly go along, maybe you can build that second dipole and build upon it. So I'm going to conclude tonight by saying that my presentation was a short video that I put together from that movie Contact with Jodie Foster. I took some segments out, I put some background music in. What I felt like when I listened to my first radio storm from Jupiter. So I thank you everybody for having me tonight. Enjoy the video. Thank you, everyone. Hope you enjoyed the talk. Take questions or.
Yeah. So.
Get ready.
All right, thanks, Don. That was great. Any questions?
Luke?
Yeah, so, for you. So we started with today's meeting with one of our members doing true science, if you will, with relatively amateur equipment. So my question is, can these antennas be used for actual science, or is it really?
Absolutely. The NASA website will have you to be able to log your antenna. You can really do a deep dive into this. Again, I skimmed the surface for fun just to pick up Radio Jupiter. But the data that you get in your backyard, you can apply it to the Radio Joe project, part of NASA. Yes, your answer is absolutely yes.
Right.
But again, I'm a little bit shy with my setup and I didn't really get officially online to publicize my data yet. After all these years, I'm shy. Any other questions? All right, up in the front here, I have, oh, I'm sorry.
Yeah, quick comment and question. The Astronomy League has a radio astronomy observing program.
Mhm.
3 levels. Radio Joe is one of their choirs.
Is it? Yeah.
And what's in the combiner box?
Well, again, it's that for ham radio operators, they'd be able to tell there are probably coils in a coupler. You're saying about the coupler, the 2 dipoles. That's a little bit of magic radio stuff. I don't want to get into that too much of that. There are probably some LC circuits in there or something to keep the impedance matching and all that. If you remember your back of your antenna on your TV, it had this dual radio feed, but then you had to convert this to coax. Well, again, that's a little bit more magic electronics inside the box. So just stick with it. It's just a converter. You don't want to, I don't want to be too much of a deep dive. But what I just wanted to say is on the front ledge here, there's information about all the websites that I put up and how to get started and to join this IO group site. And then there is copies of that Inquirer newspaper article. So help yourselves to that. Any other questions?
Others? I have a question. What's special about 20 megahertz? Why do you use that instead of something else?
Well, do you remember back in 1955, they were looking at the Crab Nebula at 22 megahertz, and they thought it was local interference at 20 megahertz. That just how it happens that's what Jupiter radiates. I don't want to get in. I mean, I don't really know the physics of it, what's going on. We still don't understand those 3 anomalies, A, B, and C, of what's really causing that. We think it's down to the core of Jupiter, but why 20 megahertz? Don't know. It just happens to be that in my answer. There might be an answer for that, but I don't know it.
I wonder if there's some coincidences there, because Carl Jansky did his first observations of the galactic center at 21 megahertz. But apparently the reason for that was the length of the pipes that was available in the store.
Microwave background, right? Yeah, there you go. And yeah, it seems like a lot of this phenomena, celestial phenomena, happens at this low frequency. But because it's 20 megahertz, big stuff, big antennas, unfortunately. So
Others? Ken?
I said I'd comment. I was at a NASA seminar a while ago, and I never realized this, and they were talking about the Europa Clipper mission. The actual magnetic field of Jupiter is something like 20,000 times that of the Earth. So it's just amazing when you think about it. That the reason they were talking about that is the Europa Clipper cannot stay in orbit too close to Jupiter for too long, or all of the circuits will be fried. In fact, they just recently, before they launched, realized they didn't actually they didn't test them adequately.
yeah, well, this is why IO is so active. there's no craters like the moon on Io. The surface is changing. It's very volcanic because it's interfering or interfacing with that strong magnetic field of Jupiter. And Io is just being stretched, shrunk, stretched, torn apart. And it's what makes it so volcanic because those fields are so strong in that area, which also causes that plasma torus of electrons around Jupiter. The electrons are just ripped apart. It's a violent area that I don't think any spacecraft could survive. Like you said, they have to be further out. All right, the next meeting, I want to see some spectrographs. All right, those IOBs only occur about once or twice a month. So you get that software, try it. It's really exhilarating to hear a live broadcast from the center of the solar system. It's really cool.
You ready for the test?
Oh, yeah, that's right. Nobody leaves. What was that velocity factor? What was that constant for a dipole?
Okay, now I would venture a guess that it's time for our raffle.
I want to thank everybody. We sold about 40 tickets tonight. So I thought that we would pick 10 out for
Okay,
10 winners tonight. We've
Wanna get
got
on the
lots of
computer?
equipment back there, good equipment, some apparel, as well as some books. So remember, if your number is called, meet me at the back table. You've got a choice of anything on the table, if your number's called. So I'll let Jan pull the numbers as an unbiased person, so.
okay, we have 378-450.
Check your numbers, okay?
Three, 7, 8. I guess they're all gonna be 3, 7, 8. So I'll just read the last three. 4, 6, 8.
468.
That's me.
Okay.
This isn't six.
Our guest speaker gets one. That's him.
446. And you're welcome to go back and check things out if you're
Yeah,
one of the winners.
446.
455.
455. Good.
481.
481.
460.
460.
Oh, that's me again.
Okay, got you.
Yes.
478.
478. How many do we have so far?
We have. Seven, so 3 more.
7, so 3 more.
447.
447.
Somebody's gotta have.
Somebody's got that. Oh, good, our student here.
452.
452.
Excellent. One more. 461.
461. Right. He's got 20.
I bought so many.
Yeah, he bought 12, I think so. Okay. Thank you all very much again. So appreciate it.
And thanks, Joe, for running this month's raffle. Yeah, there's the winners. And I want to thank you all for coming out. We'll see you next month at Fort Washington State Park for a picnic. And you want to say anything else about anything else?
That's it.
Okay. We have merchandise actually, yes, to give out. Is that right?
Well, they've been picking it up.
Okay, they have been, right. So if you purchase DVAA merchandise and haven't picked up your order, see Tom, he'll have something for you.
And we also wanted to mention, people hadn't heard, James Lovell died today. So that's a sad thing. What a great pioneer he was. Yeah. Okay, so see you next month.